Ok.
Questo dove cazzo c'è? Vabbè, un giorno la vale. Oggi è... Cioè, perché io non ho un problema. Dico nel senso, vabbè, ma vabbè, no? Tu poi, tanto la registrazione è cominciata. Le cose fare, non comincia.
Yes. Okay. Good morning, everyone. So people on the web. So today I'm gonna recap quickly the notion of capacity of the last time, and also I will introduce the relative version, that is the version we are gonna work with. So it was like the notion of capacity. So the classical notion, still a notion of 2010, is the capacity, so given theta, a big form, then the capacity with respect to theta of any Borel subset in X is defined, so we saw that it's defined as the supremum of the integral over E, the set of theta u to the power n, so the motion per measure of u, where u is of course a theta Bessage function, because we want to be able, we want to be able to define the motion per of u, and I asked you to be between d theta minus 1 and d theta. Okay, so now what we are gonna introduce is the relative capacity, where relative means with respect to a potential phi that is modeled. So we are going to replace in the definition, like in the formal way, we are going to replace phi with v theta with phi. So the definition, we follow this naive thing, is cap phi theta phi. If you want, you have to add phi of E is the supremum of the integral over E of theta u to the power n, where u is theta psh, and now u is bounded is in between phi minus 1 and phi. So you see, I replaced phi v theta with phi. Okay? And then what it turns out that, I mean, it's not trivial, but it can be proved. Actually, this is what we proved with Tamash and Chin. It was around 2020, 2021. The relative, so this is the naive statement. I'm going to write also the more precise properties. So the relative capacity, so given phi model, the relative capacity cap theta phi satisfy as the same properties of the classical one. So what do I mean? More precisely, I'm gonna like make a list like precisely of the properties I mentioned and discussed on Monday. So we have that the capacity of theta phi of E is less or equal than the capacity of theta phi of E prime whenever E is contained in E prime, to correct subset. Then the capacity of theta and phi of P is 0 if and only if P is pluripolar. So again, we have this characterization of pluripolar sets. Then again, once again, there are the sets contained in the minus infinity locus of a quasi-plurisupermodic function. Okay, and what else? Maybe this one, so we can compare there is like a comparison capacity. I'm not going to write that down, or maybe I can write the capacity, the integral over E of theta phi to the power n is less or equal than the capacity of theta phi of E for n equal n. Okay, so I mean I made a complete list last time with all the properties of the classical capacity. You can just replace that properties and add the phi here, okay? And this is also important, by the way, for these properties, for all these properties to hold, that phi is model with mass, strictly positive mass. But this is always our assumption. Remember, like at some point when I introduce this motion pair mass, I said that we are always going to work with strictly positive mass. The zero mass case is not, it's not clear yet. So always positive mass, and life is easier, let's say. Okay. So this is the relative version, and once again, like the capacity or the relative version of the capacity is the right notion to work with when we work with the motion pair operator, because of this property. So both do not charge pluripolar sets. Okay, so this is all I want to say for the moment about capacities. So you have to remember, especially I suggest that you keep in mind this property here, because it's very important. And now what I'm gonna do is like, so we are going in the direction of solving motion pair equation with prescribed singularities, prescribed by phi, the model potential. But first, I'm gonna like make a statement, and also I'm gonna prove it, that is about the C0 estimate, so a relative version of the C0 estimate that generalized both Yau C0 estimate in his proof of the Calabi conjecture, and also a version due to Koroji. So let me write things down. I'm gonna be more clear. But the statement, I'm gonna write it down. Is kind of crucial in what I'm gonna say in the following for the resolution of motion pair equation. And it uses it generalized ideas coming from the 90s. Oh, okay. Voila. Okay. So theorem. This is again Tamas group. It was proved by Tamas, Jean, and myself in 2020, 2021. So and then it says fix A in between 0 and 1, and capital A positive. Then fix also phi, the model potential with positive mass. Model and f, a positive function in LP with respect to the bag, so the Geller form on X, for some p significantly bigger than 1. Moreover, we assume that there exists u. We assume that u is function in P stage, normalize again with sup equal to 0. I told you most of the times I normalize with sup equal to 0, such that theta of u to the power m is bounded above by f omega n plus a times theta phi to the power n. So here we are assuming, so I gave you two numbers, one and two. I gave you a model potential, I gave you a density, and then I say, okay, we assume that we have a theta pluribus harmonic function u satisfying this property at the level of measures. Then what I can prove is that u is bounded above by 0 because the sup is 0, so this is trivial, but it's bounded below by phi, the model potential, minus a constant that depends on the norm, the LP norm of f, on p, on n, the dimension of the manifold, on omega, and on 1 minus a, on better 1 divided 1 minus a. Maybe I should write bigger, this is important. So let me write the same thing bigger, okay? Phi minus constant that depends on the LP norm, on p, on n, on omega, and the 1 divided 1 minus a, and it is less or equal than u. Okay, so first remark. The first.
So what is the role of big A?
What? Ah, capital A. Sorry.
Capital A.
I'm gonna tell you later. I'm gonna make, because I wanna, in my mind, while I was writing, I wanna make two different.
Okay.
So there is no capital A at the moment. Just to make things like less complicated. But anyway, so this theorem is saying, it's telling me if the motion per measure of u is bounded above by something, so we have like an information on the mass, on the volume, then we have an information on the lower bound of u. And this is actually telling me that u has the same singularity type of phi. More or less. Okay? So it's gonna be so what the second remark I want to make is that this constant here depends, this is why I wrote explicitly, it depends on 1 dividing 1 minus a. So it goes to, it blows up to plus infinity when a goes to 1. So we really need that a is strictly less than 1. Okay? We really need that a very small, okay, in applications. Okay, third remark, that is, so remark is C blows up when A goes to 1. So in this case, it's not interesting. No, it's not interesting. And the second remark, that is like an historical remark, is that this theorem generalizes a theorem due to topology, originally due to topology, in the 90s. Okay, so maybe like this, I mean, you don't think that this is very interesting, but actually this theorem here, I mean, in the literature, especially in pluripotential theory, is kind of crucial and important because it gives, so Cologgi's theorem, it gives an alternative proof using pluripotential theory of the C0 estimate due to Yao, solving the Calabi conjecture. The Calabi conjecture was in the 78, and the Calabi conjecture was actually the story I told you at the beginning about looking for the Keller-Einstein metric, studying the existence, uniqueness, and regularity of the Keller-Einstein metric having zero Ricci curvature. So at the beginning, the geometric motivation for this motion pair equation was to look for special metric with prescribed curvature. And this one was one of the cases in the Calabi-Yau case. So really, all of this is related. And actually, this theorem is the starting point that made people think that pluripotential theory could be useful to treat these geometric problems. Anyhow, so now we're gonna play a game. So now it's a game, but I can assure you that people are quite scared about that. We have all the ingredients we need right now. So we start here. We start with a lemma. Maybe here I have to make also another assumption. I also, moreover, assume u blah blah blah, such that I have to make an assumption I forgot. Pu is less singular than 5. So we're gonna have this assumption, is gonna be clear why. Following. Anyway, the lemma says the following. It says that if phi is a model potential with strictly positive mass, so the mass of phi is strictly positive, and F is in LP of x of omega n for something bigger, strictly bigger than 1. Then there exists a capital A positive. This is where capital A is gonna be, such that the integral over E of f omega n is bounded above by the relative capacity theta of phi of E to the power 2 for any E for a subset in S. So this is a lemma we are going to use in the theorem. Yeah, sure. So the lemma says if you take this model potential, you take a density, then there exists a constant such that the mass of E with respect to this measure is bounded above by a constant times the capacity at the power 2. And this power 2 is crucial. I'm going to tell you why, okay? So you could have 1 plus alpha with positive alpha. You could replace this if you want to generalize. But you cannot go less or equal than 1, okay? So you need really 1 plus alpha. 2 is much better. Huh? So this could be replaced with this slightly generalized exponent, but then let's try to keep in mind the ideas. Okay. So let me tell you that in this lemma it's important that phi is modeled. Okay. Okay. So the lemma is here, and now we are going to start the proof of this theorem. Proof of the theorem. So I'm going to define g of t. So a function of t, t is a positive real number, that is defined as the relative capacity of theta of phi to the power 1 over n of the set u less than phi minus t. What?
U is the that
Yes.
guy. Okay.
So this is a lemma. Stay there. Now we're gonna prove the theorem.
Assuming the lemma.
Yes, I'm not gonna prove the lemma,
No.
even if it's not difficult. Not proof, at least for the moment.
Okay.
Okay. Okay. This is the function g of t, and then I'm gonna start with an idea. Okay. So I'm gonna start with an idea that I'm gonna erase just to so the idea. Okay. The idea is that we want to prove that there exists a t infinity, the time very, very, very large, such that g of t is equal to 0 for any t bigger or equal than t infinity. So we want to prove that like there exists a time from where the function is 0. So this is the point. Because this would imply that, for example, in particular, g of t infinity is equal to 0. Why not? And then this implies that the capacity of this guy, u less than phi minus t infinity, is equal to 0, right? But then this means that this set is a pluripolar set, right? Because this one is the characterization of the capacity. So this guy here is pluripolar, and this means that u is greater or equal than phi minus t infinity almost everywhere. Almost everywhere outside this pluripolar set. Almost everywhere. But this you have to believe me, u and capital phi are both theta plurisupermonic function. And for theta plurisupermonic function, almost everywhere means everywhere, because they are both upper semi-continuous. So the upper semi-continuity is going to tell us that almost everywhere ends everywhere, because u and phi are upper semi-continuous, okay? Upper semi-continuous. So look at this. We proved that, I mean, if we prove that g of t is equal to 0 for a sufficiently large time, we prove that u is bounded below by phi minus t infinity. And look about the statement, this is exactly the statement, right? And then, like in the proof, it's going to be clear why this constant depends on all these quantities. So this is like, the idea is very, very easy, but then we have to make things work. Remember also the theorem. The theorem says that this piece is bounded by the capacity, the piece with the density in a p with p bigger than 1. Okay, so I'm going to erase this. So maybe I can write it almost everywhere, it means everywhere. Okay, so this is the idea. We define this this function, and maybe like a last bit of so actually what we want to prove, our goal is to prove that for any s in between 0 and 1, s to the power s g of t plus s, so t is positive, is bounded by a constant b times g of t to the power 2. So here again you see this power 2, there was the 2 appearing in the lemma, okay? It's the same power. Okay, so again, this is the same power, so it could be replaced by 1 plus alpha with alpha positive. Okay? So why this is the goal? Because actually one can prove, but this is really like one can prove what is the goal, because one can prove that if you have, so this is something for real value function. If you have a function on the real line, if you have a function g from n plus to n plus, that is the decreasing right continuous, and such that g of plus infinity, meaning the limit for t that goes to plus infinity of g of t, is equal to 0, and such that with this, satisfying this inequality, satisfying star, then there exists a t infinity such that g of t is equal to 0 for any t bigger or equal than t infinity. So this is something that holds for any function from L plus to L plus, satisfying this property. And this is kind of, I mean, this is an exercise. You have to solve all of this. So why, so now we are going backward, because I would like really to understand you what we are, why we want to do this. So this is what we are going to prove. So why this is sufficient in the case where G is the capacity. Let's look at this. So G is we want a function from L plus to from L plus to L plus, but okay, G defined like this, we take T positive, is gonna give a positive number because the capacity is always positive. So the first assumption is satisfied. Then it's decreasing. Well, it's decreasing because this set is decreasing when t is increasing. So it's decreasing. Is right continuous is something to check, but it's not very hard. And then we want that g of plus infinity is equal to 0. But the capacity of u less than minus infinity is equal to the capacity of u equal to minus infinity. So this is a pluripolar set, hence the capacity of a pluripolar, and the capacity of a pluripolar set is 0. So let me write it down. Maybe it's better. So I can erase here because we understand what we want to do. So let me write it down. Observations, okay? G of t defined here is such that G is from a plus to a plus, is decreasing because, I'm just writing down again, because u, the set of u less or equal than minus t1 is contained in u less than phi minus t2 for any t2 or t1 such that t2 is less than t1. And moreover, the g of plus infinity is the capacity with respect to theta and phi to the power 1 over n of the set u less than phi minus infinity. So it's just minus.
Not quite. You have to prove that the decreasing family of sets the capacity. I mean, if you let t going to minus infinity, means that you have a sequence of subsets, one inside the other.
Yeah.
But the intersection is just equal to minus infinity.
Yes. Yeah, but
and then
yes.
One should prove the capacity decreases to the right guy. Is it obvious? Is this obvious?
No, the capacity is decreasing. So this is the problem.
No, I mean, say sequence En of steps.
Yeah, E here, ET is
Yes.
this set.
So
U5.
if ES is inside ET, and then the intersection of all
So
of them.
ET is decreasing the intersection when T goes to from 0 to plus infinity.
This
So
is equal to.
this is this.
Okay, but then the capacity of the
Yeah, the limit of the capacity of AT is going to be equal to the capacity of S. Yes. But this is something that is proved when we look at all the properties of the capacity.
Okay.
Yeah. So this is just
Okay.
an idea of.
Okay.
So this is the capacity of this set, but this is a pluripolar set, and the capacity is 0.
Okay.
So this is the idea. Because.
And I guess you prove the right continuity in the same way.
Yes. Is pluripolar. Yes, exactly. Okay, so again, let's look at the blackboard. We said that I hope I convinced you that we need to prove that this function is gonna vanish after some time. Then here I told you that the goal is to prove this inequality for that particular function, because for general function in F plus, this is what is true. So we wanna use this statement, and over there I just checked that this condition, and this condition are satisfied because of by the properties of the capacity. So the real thing to prove, and this is the real thing of the theorem, is to prove this inequality. So this is the crucial point. This is all I want. Really, I wanna convey. Crucial. And this is what we are gonna prove in our special case of capacity to the power 1 over n. Okay. So now we're gonna do that. Okay, so we want to do that. Now I'm gonna just state a lemma that we are gonna use, and if we have time, I would like to come back on the proof of this. And this is it's called the comparison principle. So in these lectures, I mentioned the maximum principle, the domination principle, and this is the third principle, the comparison principle. And all the three of them are used in pluripotential theory everywhere, really. So they are really the fundamentals. So let me write it down. The statement in its full. This is the proof. It's gonna be later on. What did I write here? Voila. Okay. So we take. So this is a general version of it, like the most general version that is available right now. And this is the DDL. And you take two PSH functions such that, and now you see this condition appearing again. P of u is less singular than B. Remember, we have a similar condition in the statement of the theorem, just to make the connection. Then the integral over the set u less or equal than B, then theta b to the power n is less or equal than the mass over the same set of theta u to the power n. So at first sight, this could be one could say, maybe the other way around, you got totally wrong. But actually, this is really the thing. Look at this. So you take a function u less than b. So for example, 2 convex function, right? So this is u and this is v, right? And then look. So the motion per measure of u on this set is smaller than the other. Okay? So it's really this inequality. So the u is here, the u is here. And you need this condition, okay? Okay, now we are ready. Let's go for it. Let's go for it. So we take S in between 0 and 1, and we are gonna prove star, okay? So we start with an observation. So we take S, we take V in a candidate in the definition of capacity theta phi. So you take something that is PSH, theta PSH, and it is bounded by phi minus 1 and phi. So you look at S to the power n, the integral over u less than phi minus t minus s of what? Theta v to the power n. So let's look why I wrote this quantity down. First of all, so this minus t minus s is because here we want to make appear g of t plus s, right? So it would be minus t minus s, and here I have this s to the power n because actually I'm elevating to the power n both sides, okay, to get just the capacity. But it's gonna be clear in a moment. Anyway, this is the thing, and now I'm gonna play with the set. This is equal to the set u or less than 1 minus s phi plus s of phi minus t minus s, right? But yes. So let me use the power of the blackboard and put these s together. So this is s of phi minus 1 minus t, right? I didn't do nothing. And now we know that v is bigger than this function, right? So it means that this set is contained on the set u less than 1 minus s capital phi plus sv minus t. This is a game. So really, if you wanna skip this, I mean, it's like you can rest a bit, but I wanna show you all the details because it's really a game. So then this is less or equal than s to the power n, and this is the set u less than 1 minus s phi plus s of v minus t. And this is theta v to the power n. So let me erase here, and just let me remind you, maybe here or maybe up here, okay, that the goal is to prove something like this for some b. Okay, this is the goal. Anyhow. So here we are, and now I'm gonna like let you observe that if you take the motion per measure of 1 minus s phi plus fb, this is by definition, just rewriting things, is 1 minus s of theta phi, so theta plus the c of phi, plus s theta of v. I mean, you can write it down and then you can check. Oh, but this is, I'm just rewriting things to the power n. And then here I have two positive quantities to the power n. If you want, you can use Newton, and then you can see that this is greater or equal than just this term to the power n. Okay. Again. And this means that this
These
gap,
are positive objects.
yeah, because they are positive objects, otherwise it's not true. So this is less or equal than the integral over this big set of what? Of all this motion per measure. We are replacing Sn theta Bn, all of this. Okay. And now look, I mean, and then if you want to, you can also add minus t, because minus t is a constant. So
okay.
you don't see that in the motion part. And then look at this. So here we have something that now we want to use the comparison principle with u equal to u and the v there, all this function. Why we can use the comparison principle that I call the CP for comparison principle. In order to use that, we need to prove that the envelope of u is less singular than v, right? But this is true because the envelope of u is less or equal, is less singular than phi by assumption. Hence, it's less singular than all of this because phi and v has the same singularity because v is bounded by phi, above and below. And this has the same singularity of 1 over minus s phi plus s.
Because this phi is 1 smaller than the.
Yes, because of this. Because this is a candidate in the capacity. Anyway, I just want to make sure that all the assumptions were satisfied, so we can use the comparison principle. And this says that the mass of the bigger guy on the set is less or equal than the mass of the smaller guy on the same set. Okay, now I'm going to use again the power of the blackboard. V is less or equal than phi. So this set is contained in the set where here I'm going to put a phi. And then 1 minus s phi plus s phi, just phi again. So this is phi. Minus t, yes, sure. Okay, so let me write it down what I end up with. I end up with this guy here. This guy here, I mean, this is really what we proved, is less or equal than this guy. And this guy here, so now we're going to take the supremum, taking the supremum over all the candidates in the capacity over V. So if you take the supremum over V, you get Sn times the capacity of this set. So you get Sn times the capacity theta phi of which set? U less than capital phi minus t minus s. And on the other side, you get this. Okay, so what you got? So you see now things are starting coming up, right? Because you got the S of n gt to the power n. Gt plus s to the power n is less or equal than something that involves the motion per measure of u. So now we want to control this guy. Let's control this guy. So this guy, by assumption, is less or equal, now we're going to use the assumption of the theorem, is less or equal than f omega n over this set plus a times theta phi to the power n over the same set. Okay. Okay, very good. Yes, okay, perfect. And this set here, so let me rewrite it down again. So this set is dominated by the capacity. So it's A times the capacity with respect to theta and phi of u less than phi t to the power 2. This was because of the lemma. Because f is an LP, because f is an LP for p bigger than 1 and capital phi is model. And this other term here, a blah blah blah. So for this other term, we're going to use the comparison principle again, and we get that this is less or equal than a times the mass with respect to the smaller guy, that is u. So again, and this is the comparison principle. So this is u, and on the same set. So here is comparison principle. CP. Okay, almost there, almost there, almost there. Why? Look at the blackboard. You got that the mass of theta u to the power n of a set is bounded above by a constant time the capacity at the right power, plus a coefficient, the same quantity that is on the left-hand side. So we are going to go on the other side. I'm going to be here. I'm going to be here. So what we end up with is that 1 minus a, the mass of theta u, where u is less than phi minus t, is less or equal than a times the relative capacity of the same set to the power 2. Then we divide, because a was strictly less than 1, and then here you see why this is coming up. And you got this. Okay? But then, okay, we are gonna just put together this inequality and this inequality. So this is gonna be 2b, and this is gonna be small a. This inequality over here. We combine the two together, a plus b, and we get that S of n times the relative capacity of the set u less than phi minus t minus s to the power, no power, is less or equal than a times 1 over small a, the relative capacity, this guy, to the power 2. Okay? So this guy. So, and now if we rewrite things, in terms of G, we prove that S, G of T plus S, is less or equal than A, capital A divided by 1 minus small a to the power 1 divided by n times G of T.
But no, okay.
I'm dividing everything to the power 1 over n to get G, right? So I have to divide it. But then I have the 2. Okay, so look at this. This is wonderful. This is exactly what we wanted to prove with B equal to capital A divided 1 minus A.
The one over.
Okay. This is exactly what we wanted to prove. Okay, so I really think that this is a good moment to make a break, to stop. But then, I mean, the point that I want to make is really we proved the theorem. Okay, so we proved the super generalized version of Cologi's theorem. And I mean, once we had all the ingredients, this was just a game. So understanding that the idea was actually to prove this inequality. But then, of course, Have you saw that? I mean, it's a game if you understand how to compare and combine things in a clever way, right? Okay, I'm gonna stop here. If you have questions, we can use this break for the questions. I hope you are also happy, Stefano. I don't know if you ever saw the if you ever saw the proof of this. Yes, let's make a quick break. And after maybe, so we're gonna make a so let's take a break. But the only thing I would like also to do today, to finishing up, is to prove like the comparison principle, this thing that we use a lot in a crucial way. Because as I told you, the maximum principle, the denomination principle, the comparison principle, they are crucial. I didn't prove the first two, so let me prove at least the third. But it's really the one that is like, let's say that the comparison principle is going to be the denomination. They are related, so proving one is already like a good thing. Okay. If you have questions, yes, sure.
In this lemma, your P can be infinite or not?
Say it again.
P can be infinite.
B.
P.
P.
F is an element of LP.
Yeah, sure. You can take bounded density. Yeah. So P is in between 1 that you don't take, so strictly bigger than 1, and plus infinity that you can take.
Is there any particular reason for defining G with the exponent 1 over n?
Just to have a nicer inequality here. To prove, you remember at some point I gave you a very general lemma that holds in R on the real line for a function G, right? It was like given G from R plus to R plus such that G is right continuous, the limit when t goes to plus infinity is 0 and decreasing, and solving this inequality, then you get you get what you want. You get the G of t is equal to 0 for large time. And now I want just to, so this is why I need 1 over n here to get the G, because this inequality is equal, this inequality as I wrote up there is equal for G with the power. But then, no, it's just for beauty if you want. So there is no particular reason. You can erase at the power n everywhere. But then it means that you have, if you do that, so if you do that, for example, this is what you want to do, right? If you want to do that, you have to prove this. With s to the power n.
This is just then also then is the dimension of
the game?
It
depends. Everything it depends on the dimension. You remember the constant of the theorem. It depends on the dimension, of course. We are using the dimension, but this is fixed.
No, because I mean in this function G, the fact that n is the dimension is important. Or?
Yeah, it's important. It's important because this n is coming. I mean, the thing is that when you look at this guy, you are saying that this is less or equal than 1 minus s theta phi plus s theta p to the power n. So here you really want the dimension. This is true only for n the dimension.
Oh.
Okay?
Okay, right.
You're welcome. So this is why you really need the dimension. Does this answer?
Yes.
Here. Yes, we can take other couple of minutes. Stefano?
Yes. Yes.
Do you also have any requirements of what you would like to see?
Well, comparison of principles are
Okay. I'm gonna, I have some time, so I can prove it in very, very general motion. How do you use it to start slowly?
Okay.
Devo esaminare uno fa, pessima qualità della rete, o cosa?
Lo dico sempre che devi fare il mondo.
Ok. Okay. Okay, I'm gonna use the bridge. Okay. What? Okay. Comparison. So this is the thing we are gonna end up with. Proof. As I say, that it's fundamental. And then we are gonna see what the crucial ingredient is, which is gonna understand better this relative theory. So when I say relative, it's with respect to this model potential. So comparison principle. I'm gonna again state the theorem in its full version, full generalization. So I take two functions. Theta PSH such that Q of U is less singular than B, then, as we say, the integral over U less than B of theta B to the power n is less or equal than theta U to the power n on the same set. So this is what we are going to prove. So we are going to start the proof with, we are going to do two cases. So the first case, we are going to prove the comparison principle for U and B theta PSH, but both in the class, in the same class E of capital phi. So we assume, for the first time, assume there exists phi such that, okay? Model such that.
Model phi.
Yeah. So this is the first assumption. We are going to assume that both of them are in the same class E with respect to a model potential. Okay, what does it mean? So this is the first step. Okay, first step. What does it mean being in the class E? It means that the integral, let me write it down. So theta u to the power n over x is equal to the integral over x of theta b to the power n. That is also equal to the integral over x of theta phi to the power n. Right? This is definition of class E. So they all have the same mass. Okay. And now, also observation. If you take the maximum in between u and v are still, we already say that, we noticed a lot of time, still a theta PSH function. So the max is an operation that preserves the quasi-truth of harmonicity. And also, so look at this, the maximum between u and v is gonna still be in the class E of x, theta, and capital phi. And also it's gonna be in the same class.
Is it obvious?
Because the maximum of this, so this function here is gonna be bounded above and below by either u minus a constant and u plus a constant, or v minus a constant and v plus a constant.
But you're here, not bound.
So being here, being here, it means that u and v have the same mass of this, and also they are less singular than capital phi. Okay? So if u and v are more singular than capital phi, also the maximum between u and v is more singular than capital phi. But a priori, since this is the maximum, it's so. Okay, let me. You want me to explain this, okay? Why is that? So let me prove this first thing. So since these two are less singular than phi, then the maximum is again less singular than phi, right? Okay. But also the maximum, so a priori, so this implies that the mass of this guy, of the maximum, is less or equal than the mass of phi. This is because this is less singular. We say that the mass preserves, the volume preserves the inequality. But also the maximum of u and phi is less singular than u, if you want, of v, because it's a maximum, right? So it's bigger, even bigger, okay? So a priori, you have that this guy, the mass, okay? Let me write it down. The mass is greater or equal than the mass of theta u. But these are the same. So everything has to be in equality, and this is the thing. It's a game. Again, it's a game. But okay, so we proved that. Very good. Here. Let me be here, and then I'm gonna erase this. So it's the class E, and then we got that the mass of this is also equal to the mass of phi, of the mass of u, whatever you want, all are the same, is also, look at this, greater or equal than the mass of the same guy. So we are going to divide the set X in where U is strictly smaller than B, and where B is strictly smaller than U of the same guy. So why this is bigger or equal? Because look at this. The union of these two sets is not X, is missing, the contact set is missing. So this is why we got the inequality there. Okay? So this plus this is strictly containing X. Okay? But then here we are going to use the maximum principle. So the maximum principle is going to tell me that when U is strictly less than B, the maximum between U and B is B. And here I can replace B. You remember this was the locality of the motion per measure. So this is U less than B. I can replace U here inside. And the other side, this is B, because B is bigger. And here is U. Okay? Okay, now look at this. This is theta B to the power n, U minus V, plus, and this is what? This is now this set. I can say that this is the mass over X minus the mass over the complementary. So U less or equal than B. I wrote X as the union of these two. So this is what I've done. Okay, very good. But then, as I said at the beginning, also this guy is equal to the mass of U because they are all in the same class E. Okay? And now this you can erase, you got the cancellation. So you get that this quantity here is negative. Here you get 0. So you got that 0 is greater or equal than the integral over U less than B on theta B minus the integral over U theta U to the power n. And this means, I'm going to write it here. I'm just rewriting this inequality. This means that the integral of theta B to the power n over U less than B is less or equal than the integral of theta U of U less or equal than B. Right? It's exactly this. So, and this is the comparison, exactly the comparison principle up to, here we have strictly less, and here we have the inequality. But in order to arrange that, instead of U, you're gonna work with U plus epsilon, with epsilon positive, and you get the same statement with U plus epsilon strictly less or equal than B, but this means U strictly less than B. You let epsilon goes to 0 and then you get this. Okay? So this is really like just a smaller thing, that's just to tell you that I'm not cheating, okay? Anyway, so here is the comparison principle in the case where the two.
But the first part, U plus epsilon smaller than B.
U plus epsilon smaller than B, and then you let epsilon goes to 0, and then you get U less than B.
And then you get U smaller or equal, also the other side.
Less or equal.
Now, yeah, apply this guy to U plus epsilon, you get that. Sorry, but okay.
U plus epsilon, but this is equal to this, and this is this. And this is true. And this is true
on both sides, no?
No, you get strictly less, but this is true for any epsilon.
Okay, but when you take the limit, it seems to me that you get u smaller or equal to b in both
Come on,
sides.
this is still even bigger than u.
Okay. U smaller than b, u smaller or equal to that. Okay.
No. This is like this, and this is you can also say that u plus epsilon the b is contained in u strictly, and this is less or equal. Not cheating. Not cheating. Not with you, Stefano.
This elementary things I get to wisdom. Okay.
But no, but these are actually this is my point today. It's like we are really proving something big using a small observation. Once we have constructed our basis, and this is one of the bases. So let me finish the proof because we are almost there, and then I want to make a point. But anyway, so I hope I convinced you that I proved the first step. So when all the two functions are in this class E. Okay? So the first step is okay. Okay, this is proved. Then this we get. Okay, and now we want to do the first step. The second step is the full version. Second step, okay? Good. So for the second step, we're gonna use u equal to u here. So u is gonna be fixed. So we use the maximum principle. The comparison principle is step 1 for u and phi that is equal to the maximum in between u and b. So why this is okay? Because this is okay, since both of these functions are in E of x, theta, and p of u. So why is that? Okay, the u is in the E class of p of u is okay. So let me write it down. So u is in E of x, theta, of p of u because u is less singular than p of u by definition, and also this is something that I proved a couple of episodes ago. The mass on the envelope is equal to the mass of u. For this, we use that p of u was constructed as an increasing limit of uc. Remember when c goes to plus infinity? And now let's look at phi. So phi is also less or equal. So phi is the maximum of u and b. So in particular, so phi is the maximum of u and b. So in particular, is bigger or equal than sorry. Okay. So phi has the same. The maximum of u and b. Yes, sorry. Okay. So this is for sure bigger or equal than b. And so b was less singular than p of u, right? And on the other, so this function here, so let's look at this function, the maximum of u and b. So in the set where the max is b, then b is less singular than p of u, so we are okay. When the max is u, then u is less singular than p of u as well. So I want to say that the maximum between these two functions is less singular than p of u as well. Because both of them are less singular. So let's say phi is more singular than p of u, because both of them, because u is more singular than p of u, and v is more singular than p of u. This is my point.
And then why this
What? This is the assumption. Over there.
Okay.
This is the assumption. And
Okay.
this is the construction.
Okay. And the fact that they're both in E is
this is because let me see what maximum of this.
okay.
No,
For you
because-
is that. For you is this one.
For you is this one, and for the other is again. So you are convinced that phi is less singular than p of u.
Okay.
You are convinced.
Yeah.
Okay. So this means that the mass of phi is again, once again, the same. The mass of phi is less or equal than the mass of p of u, right?
Okay.
But this is equal to the mass of u.
Okay.
But this
But
was
this
the mass. So a priori, this is greater or equal than the mass of u, because this is bigger than u. Hence equality. Okay? It's always the same game. We just to choose our battle. Okay, so I hope that I convinced you that these are in this class E. Okay. And then you saw also where this assumption is necessary, okay? This assumption is necessary to prove that phi is in this class E. Okay, but then what we have, for the first step, we got that u less than phi, u less than phi of theta phi to the power n is less or equal than theta b to the power n, sorry, theta u to the power n, u less than phi, right? But phi, now we are using, so here we are using that.
But you is always less than 5.
Strictly less. No, strictly less is not always less than 5.
Okay.
You have the contact set. And also you have V that you cannot control. So I want to say that this set here, so u strictly less than V. Oh, sorry. Okay. Maybe let me start with this set here. So if you want, this is what you were saying, Stefano. This is equal to this. This is exactly equal to this because phi is the maximum between u and b. When it's equal to u, this is empty, and when it's equal to b, this is the set. So this is what you were saying. And we have this. And on the other side, you got the same. Theta phi n, where u is bigger than b. But then again, you use the maximum principle, because phi is equal to b on the set u strictly less than b. So the maximum principle is going to tell you that here you can replace b instead of phi. So this is the maximum principle. So you got that the integral over u strictly less than b of theta b to the power n is less or equal than the integral of theta u to the power n on the same set. And this is what we wanted to do. So this is this is the real thing to prove. The second step is just like we really use the first step and that's it. Huh? But the thing I would like to conclude my point is that if you go into the proof, you really see that we play the game using the fact that we know three things. We knew that the mass of the singularity type was equal to the function of the beginning. That we knew that, and that's that we knew that if two functions have the same singularity type, the mass is the same. And if you have an inequality, a function more singular than the other, then the inequality was preserved at the level of masses. This is the only thing.
You said twice the same thing, yeah?
Once is the with two in it, yes. Yes. But then and all of this in like a less general version of what I said. So these three building blocks were no, not all of this, but some of these were proved by David Winistrom. So this is what I said to you when I like a couple of lectures ago. So this is a paper of 2017, and when we saw this, we saw the crucial statement. If you wanna like to sum up, the crucial thing that we use for this comparison principle and all these general things, like at the very earth, is that if two functions, one function is more singular than another, then you get this inequality at the level of masses. Summing up, this is really actually what we proved. I'm building up from this. So this is what proved by Winistrom in 2017. This is something also that I tried to prove in my PhD thesis, but I didn't succeed. And when we saw this, we said, okay, come on, we can do a lot of things. So this was something that it was missing, and we couldn't be able to prove. And then actually, then we re-proved and we proved like much more general versions of it. Okay, so I think this is a good point to stop.
Very good.
Do you have questions? Is that okay? People on the web, on Teams, do you have questions?
I'm fine for questions. Thanks, Eleanor.
No? Yes or no? No. Okay. Okay. Then thank you to be there.
Okay.
See you Monday.
Okay. See you on Monday. Ciao, ciao, ciao.
Ciao. Ciao.
Ciao, ciao a tutti.
Chiudo.
Ciao.